Okay, so let us start. So I have discussed about the moment of inertia yesterday, how we are going to calculate the moment of inertia. Today we are going to deal with some of the problems based on the moment of inertia. First, let me give moment of inertia. I'll give you one problem statement. You try on your own first. So let us take a rod of mass m. So find the moment of inertia of a rod of mass m about any one of its end. So can you try to solve this on your own first? Anybody got any idea? So this rod is actually rotating about this particular line. So that is one of its end. So this is holding with one of its end, and this rod is trying to rotate like this. Now what is the moment of inertia? Now here, to find out the moment of inertia, let us consider an elemental mass of delta m. So this is the elemental mass, and which is located at a distance of x. So this is at a distance of x. Now, the moment of inertia of this elemental mass about the axis, this axis is given by, so the moment of inertia of the elemental mass delta m about the line A. So I call this line as A is delta m into x square. So this is di. So the moment of inertia or the elemental moment of inertia is nothing but so x square into delta m. So this is di equal to x square into delta m. Now this delta m is dependent on this x. How it is going to be? Let me give this. So the density of the rod rho is equal to total mass by this entire length L. So I call this as L, and then this will be m by L is the density. Now out of this delta x length, so this is delta x length which is having a mass of delta m. Now this delta x length is having mass delta m, right? And then rho is nothing but the density, and then into delta x. Elemental mass delta m is equal to rho into delta x. So this is rho is nothing but m by L, or delta m is equal to m by L times of delta x. So delta m you can replace with x square into m by L times delta x. So this is di. So this you can replace as delta x tends to 0. This you can replace as I is equal to integral m by L times of x square dx. And this is varying from 0 to L. So this integration, once we solve this, this is I is equal to m by L times of x cube by 3, and the upper limit will be L and the lower limit is 0, and this is m by L times L cube by 3. So this is ml square by 3. So this is the moment of inertia. Got it? Understood? So this is actually to give you a simple idea how we are solving the moment of inertia. So the procedure is straightforward and simple. You have to identify an elemental mass, and then that elemental mass, find out the moment of inertia for that elemental mass when it is rotated about any one line. So which is having a distance of x. So delta m into x square, and that delta m you will have to convert in terms of x, then integrate it. So this is the standard procedure, whatever may be the shape it is. So if it is an area, or if it is a length, or if it is a volume, but the procedure is same. So you will be identifying the delta m value in terms of the density. So here we have considered the linear density. That's why this mass is entirely distributed equally. That means this is the density, whatever it is having is rho, is given by m by L. So m by L is the density. Suppose if it is a area shape, then it's not m by L. So m by A is the density. Suppose if it is a volume, then m by V is the density. So mass by volume is the density. That's how actually we relate the density and the mass to find out our moment of inertia. Got it? So depending upon the shape or depending upon the type of distribution it is having, you will be dividing the mass, or you will be dividing the density in terms of the mass according to the shape. Got it? Understood? Any questions on this? Any questions on this? Okay, so note down one more. Find the moment of inertia of a circular ring of mass m. Find the moment of inertia of a circular ring of mass m about an axis passing through its center and perpendicular to the plane of the ring. So can you find the moment of inertia of it? So there is a circular ring. This is the ring. So from the center, if there is an axis that is passing through like this, so about this particular chart piece, if this circular ring is rotating like this, then what is the moment of inertia of it? Anybody got the idea? Anybody got it? The procedure is straightforward and simple, right? So there is nothing different from the previous problem. I think you should be able to solve this. Anybody wanted to give a try, or you want me to solve? Okay, fine. So let me solve this. See this. So exactly the same procedure. Now actually this is a circular ring. So the mass is distributed over the periphery like this. So it's not a disc, it's a ring. So that means it's a kind of shape like this. So this is the ring. Now the mass is distributed equally throughout the ring. Then, so consider an elemental length dl, and it is having a mass of delta m or dm, and the radius of the ring is a, let us say. Then the density of the ring will be rho is equal to entire mass is m. So the mass of the ring is m divided across total perimeter, that is 2 pi r, or in this case, or I call this as r, 2 pi r. So that is the density, and this density getting multiplied by dl is nothing but dm. So the elemental mass dm is nothing but rho times of dl, but dl is nothing but this is the dl, and then it is occupying an angle of d theta. Then dl is equal to r times of d theta. So this is L is equal to r theta format, right? So for an elemental angle of delta theta, there will be arc length of delta L. So that if you replace it, this will be rho times of, and then r times of d theta. So this is the elemental mass. The moment of inertia of the elemental mass about the line passing through the center di is equal to mass into length, so square of the distance from the axis to the mass. So that is r. So this is r square dm. So that is nothing but di. Now if you want to replace dm in terms of rho, that will be, so di is equal to r square into, so dm is nothing but rho times of r times of d theta. So this is dm. Now if you integrate on either sides, this will be rho r cube d theta integral. So this will be rho r cube theta varying from, so 0 to, so this is horizontal line 0 to 360 degrees. So this is 0 to 2 pi. So this will be 2 pi times of rho r cube, and then out of rho r cube, this is m by 2 pi r is rho. So this is I is equal to 2 pi times of rho r cube. Rho can be replaced with m by 2. So this 2 pi will cancel and this will be mr square. This is the moment of inertia. Understood? Got it? Any questions on this? Now for the same problem, I hope you understood, everyone understood this. So for the same problem, now rather than the axis perpendicular to this, can you find out the moment of inertia about any one of the diameter? About the diameter for the same ring, you find out the moment of inertia. This is mr square. Tell me what it is. I think mr square by 2. Yeah, that's correct. Yeah. Anybody else? Anybody else got the answer? mr square by 2. So in the previous problem, there is only one change. Earlier actually we have taken the distance from here to here. Now actually from this axis actually you have to find out the distance. So this is nothing but r sin theta. So that's the only difference. Now here the elemental area di is nothing but rho times of dm. Rho times of. So the moment of inertia is, that is, I call this as y. Then it will be y square dm. Y square dm is the moment of inertia of the elemental particle which is considered at this particular point. Now, y is nothing but r sin theta whole square. Dm is nothing but, that is, the elemental mass. So, m by t, 2 pi r is rho, and then rho into, so this dl is nothing but r d theta. So, rho into dl is the mass, but dl is r into d theta. So this is the sequence. So here r sin theta whole square into rho times of r d theta. So this is di. Now you need to integrate this, is equal to integral rho r square r cube sin square theta d theta, varying from 0 to 2 pi. So this is the moment of inertia. Got it? So this you are going to get as, after the integration, this is mr square by 2. Now note down one more. Find the moment of inertia of a circular disc about its diameter. So now it is a circular disc. Find the moment of inertia of a circular disc about any diameter. So the mass of the circular disc is m and the radius is r. Anybody got it? So anybody else? Yeah, so mr square by 4 is correct. Anybody else got it? Anybody got the answer? Okay, so let me solve this. See this. Consider an elemental area. So this is the elemental area. So this elemental area, let us say this angle is d theta and then the radius is r. This is r. Then this arc length is given by, so let us say, or actually the radius I call as a, and then till this particular point, so this is r. Then r d theta is the arc length. So this arc length is given by r d theta, and then this length is the elemental radius change. This is dr. Then this particular area, let us say, that is dA is given by dr times r d theta. So this is r dr d theta. So this is the elemental area dA. Now the circular disk is having a mass of m. So the density of the circular disk is given by rho is divided as entire mass divided by entire area. So area of the circular disk is pi a square. So rho is nothing but m by pi a square, which is nothing but the density of the circular disk. So the mass is distributed across the area equally. And then elemental mass. The elemental mass of the elemental area delta A is given by dm is rho times of dA, but dA is r dr d theta. So this is rho times of r dr d theta. So this is the elemental mass. So for this particular one, so we are talking about the moment of inertia about any one of its diameter. That means this elemental mass is located at a height of y, but y is nothing but, this is at an angle of theta, so that is y is r cos theta, sorry, r sin theta. So the moment of inertia of the elemental mass delta m is given by di is equal to so dm into, this is the moment of inertia of the elemental mass. And then this you can replace di is equal to y is r sin theta whole square into dm is rho times of r dr d theta. So here actually r is a variable and theta is also a variable. So this one I you can get it by integrating this. So I is equal to integral over the area A rho times of r cube sin square theta dr d theta, and this A is nothing but the area identified by the circle disk. So this area r is varying from 0 to a and theta is varying from 0 to 2 pi. So this is the integral, you need to be solving it. Now this integral you can solve it. So do the integration with respect to r first, then rho times of r power 4 by 4. So this is a power 4 comes out and the lower limit is anyway 0. So a power 4 by 4 and then integral 0 to 2 pi sin square theta d theta. So integral 0 to 2 pi sin square theta d theta, it will be 4 times of, so this is rho a power 4 divided by 4 into 4 integral 0 to pi by 2 sin power 2 theta d theta. So this will be pi by 4. So this is rho a power 4 into pi by 4. So this is the moment of inertia. But rho actually you can replace as m by pi a square. So I is equal to m by pi a square into a power 4 into pi by 4. So this is pi will cancel and a square. So m a square. Yeah, that's correct. M a square by 4, right? So this is the moment of inertia. So here actually we are using a little bit extension to the normal integral. Earlier actually the mass is divided uniformly on a line. Now the mass is divided uniformly on an area. So that's why we are using double integrals. Exactly the same thing we will extend to the triple integrals if the mass is distributed over a volume. Got it? Now, can you find out the moment of inertia of the same circular disk about any of the tangents? Find the moment of inertia of the circular disk, exactly the same dimensions, but about an axis which is a tangent to the circle. Can you solve this now? Anybody else got it? Got it? So as Keshav said, so you can of the diameter, right? So take a diameter like this, then about this, the moment of inertia I is ma square by 4. So as parallel axis theorem, if there is a parallel axis which is separated by a distance here, d is a. So then it will be, moment of inertia will be, as per parallel axis theorem, m into a square plus ma square by 4. So this is 5ma square by 4. So this is the moment of inertia about the axis which is passing through the tangent. Got it? Understood? Fine? Okay. Note down one more. Find the moment of inertia of a rectangular parallel pipe about an axis passing through its center. Find the moment of inertia of a rectangular parallel pipe about an axis passing through the center and parallel to the any one of the sides, any one of the edges. So in the dimension, so this is the parallel pipe. So this is the parallel pipe, and this length, so this is, if you take the coordinate axis from the center, so this is x-axis and this is minus x. So this length is a and this is minus a. So this is minus a to plus a and plus b to minus b and then plus c to minus c. These are the dimensions of the parallel pipe. Got it? For this parallel pipe equation, find out the moment of inertia. Got it? Anybody got it? So you take the moment of inertia about x-axis in this case. So this you can take it. So x is varying from minus a to plus a, and y is varying from minus b to plus b, and z is varying from minus c to plus c. So that's how you can take it. So if this is x-axis and this is y-axis and then this is z-axis. So z is varying as minus c to plus c. Got it, Keshav? Okay, so let me solve this. So length is 2a, breadth is 2b, and height is 2c. So these are the dimensions of the block. Now the mass is, so the mass of the block is m. So density of the block rho is equal to m by volume 2a 2. This is m by 8 abc. So this is the volume. Sorry, this is the density. Once you find the density, so consider an elemental mass. So randomly we have considered the elemental mass at this particular position. So this elemental mass, right? So this is having certain length, certain width, and certain height. So that is dx, dy, dz. Dx, dy, dz is the elemental volume. So that elemental mass, so dm is given by rho times of dv. Rho times of dv. And then this dv contains dx, dy, dz. So this is the elemental volume. Now the location of the mass will be from the x-axis, because we are trying to identify the moment of inertia when it is rotated about the x-axis, which is passing through the center. So this is the center line. So this is the x-axis. When it is trying to rotate like this, then the mass, whatever is considered here, this is located, so with an x value, so with a y value and z value and x value. Now, but x doesn't matter, because the perpendicular distance from the x-axis is nothing but y square plus z square is, so the distance of the elemental mass from the x-axis will be equal to, so this is x and this point is p. So xp is equal to y square plus z square under root. I hope everybody understood this. So xp is nothing but the distance from the x-axis to the elemental mass. So this elemental mass location is x comma y comma z. But from the x-axis actually we are trying to find out the perpendicular distance. So then the perpendicular distance will be y square plus z square under root. So that will be xp. Now the moment of inertia di is given by, so xp whole square times dm. So this is y square z square times dm is, that is rho times of dx, dy, dz. Now this we need to be integrating. So I is equal to integral. So x limits are from x varying from minus a to a, y varying from minus b to p, and z varying from minus c to c. So this is rho times of y square plus z square into dx, dy, dz. So this is the moment of inertia, right? Now in this moment of inertia, rho you can take it out and then do the integration with respect to z first. Then this will be z cube integral minus a to a integral minus b to b, and this is y square z plus z cube by 3. Upper limit is c and lower limit is minus c. Got it? So then this will be c square, c plus c cube by 3, 2 times of. So 2 rho times of minus a to a minus b to b cy square plus c cube by 3 dx dy. Right? So this integral you can complete it. I think so this is straightforward, simple integration only. So you can note down this and then try to complete the integral. Tell me the final answer once you complete that. Anybody got the answer for this? Now this integral, so 2 rho and then integral minus a to a, and the integration with respect to y will be c y cube by 3 plus c cube y. Upper limit is b and lower limit is minus d. Yeah. So this integral with respect to dx, so 2 rho integral minus a to a, then cb cube by 3 plus c cube y, c cube b divided by 3, and this 2 times dx. So 4 rho by 9, then cb cube into x plus c cube b into x. So upper limit is a and lower limit is minus a. Then this will be 4 rho by 9 times of bc ac into b cube plus ab into c cube. So this will be again 2 times. So this will be 8 rho by 9. This is ABC, if you take it out, b square plus c square is left over. Now rho you can replace with rho is equal to m by 8 ABC. So just replace 8 rho by 9 times of ABC, and this rho you can replace with m by 8 ABC into b square plus c square. Now this 8 ABC will cancel out. So m by 9 times of b square plus c square. Sorry, this is only 3, right? Yeah. So 3 is taken out. So this is only 3. 9. So this is 3. So finally, the moment of inertia I we have got, that is m by 3 times of b square plus c square. So this is the moment of inertia about x-axis. Got it? Understood? So this is the moment of inertia. Now from this actually you can guess what is I. So it will be m by 9 times m by 3 times of y-axis, that is a square plus c square, and iz it will be m by 3 times of, so a square plus b square. So this is you can guess the moment of inertia. You can even verify the parallel axis theorem and perpendicular axis theorem also. Yeah. Got it? Okay, so this is about the moment of inertia. Do you have any questions on this? Any questions on this? Got it? Okay, so with this I would like to stop the class for today. So I will give you one assignment based on this, and then tomorrow I am going to start with a different topic. Yeah, so thank you and good night.